Hi everyone, welcome back to Operations Research. So we're still at our modeling and applications course, and today we're going to jump into our new topic. We will talk about nonlinear programming. So first I will do some very brief introduction, and then we will talk about two examples. In these two examples, you will naturally see the problem is nonlinear. So we really cannot use integer programming or even linear programming to deal with that. So we will go through these examples to show you, indeed, nonlinear programming may be used in some way. Okay, and then we will talk about two issues about linearization. So linearization means we are given a problem, and your first attempt to do the formulation is to make it nonlinear. You will see that in many cases, your formulation has something to do with a maximum or minimum function, or sometimes you have products or decision variables. And in that case, the program is not linear, but actually there are some ways for you to linearize it if some condition holds. Okay, so that's something we will talk about in this particular course. Okay, so let's see some very brief examples. In many cases, we want to price our products. So for example, suppose there's a retailer. The retailer is buying one product at a cost which is C. So you'd pay $5 to get one product, $10 to get another one. And then the retailer needs to decide a unit retail price, which is P. Once I do that, the demand would be given as a function of P in this way. So we would see that once we increase our price, our demand would go down in a way that is A minus BP. So A and B are two parameters. I know the values of A and B, and that somehow means, according to my past experience, I know how consumers are sensitive to my price. So I now want to do profit maximization. I want to set a price so that I can maximize my profit. So in this case, my parameters are A, B, and C. Okay? And then once I collect this information, I want to set my decision variable, which is P. The only constraint I have in this particular case is probably that, okay, my price cannot be negative. All right? I want to choose $5, $10, $12 as my unit price. I guess I cannot set a negative price. That does not make sense. And then finally, we may reach our formulation. So we want to maximize this particular function. P minus C is our sales margin. Okay? When I sell one product, I may earn P minus C dollars. For example, if I set my price to be 12 per unit, but if my cost is $5 per unit, then if I may sell one unit, I'm going to earn $7. If I can sell two units, I'm going to earn 7 times 2, $14. Okay, so this part is my sales margin, and then the other part is my demand. So my profit actually is the product of these two terms. Okay. It depends on, for each item, how much I may earn, and depends on how much I may sell. Okay, so this is my demand profit function, and the only constraint I have is P should be non-negative. Okay, so there are several ways to express this particular formulation. Sometimes we want to write it in this way, or sometimes some people will say, okay, this constraint is so simple, I'm going to put it below the maximization operator. So in either way, you understand they are talking about the same thing. So in this case, this is nonlinear, all right? Because P times P, this is P squared, and this is obviously not a linear function. So that's why we say this guy is a linear program. Let's see another example. So in this example, you are given a piece of square paper, and the length at one side is A. Okay, so A may be 10 centimeters, 12 centimeters, something like that. We now want to cut down 4 small squares here, 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 and here. And once we do that, we want to make them equal size. So this particular length would be small d. And once I do that, I'm going to fold this paper to create a container in this way. Okay? So you may see that for this particular square, that gives us the base for this particular container. And then the height of this particular container would be this small d. Alright? So this would be how I may get a container by folding my paper. So now the question is, how may we choose d, the length here? How may we choose d to maximize the total volume of the container? So again, this is a maximization problem, and again, this is an optimization problem, and all we need to do is to somehow formulate our problem to describe the quantity that we are interested in. So we all know that the volume of this particular container is the area of the base multiplied by the height. So the base would have this area a minus 2d or a minus 2d square, and then multiply it by the height. So a minus 2d square times d, that would be the volume. We want to choose a small d to maximize this volume. Okay? Again, you have square terms, you have product terms. So this is a nonlinear program. Suppose we want to locate a hospital. So in a country, there are several cities, let's say here, 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 and here. So there are many different places where we have cities, and many people live there. So for these cities, we all know their locations. For example, this one may be at 8, 3, this one may be at 7, 1, and so on and so on. So we know where they are. And then we want to locate a hospital somewhere so that we may minimize the average Euclidean distance from the cities to the hospitals. So what does that mean? Let's say I locate my hospitals here. Alright? Then in this case, I'm going to have traveling distance distance from all these cities to this particular hospital. So I may have several options. For example, maybe I want to choose the hospitals to be here. Well, if I do that, then I may see that the distance would be somewhat different. And in each setting, I would have different average Euclidean distance. Alright? So our target here is to choose a facility, choose a location to build our facility. And then we want to minimize the average Euclidean distance. So how may we do that? We have n cities. For each city, I know its location. I also know where to build my facility. Okay, I'm going to build it at somewhere, x, y. Once I have that, then this particular thing would be the Euclidean distance from my hospital to city I. And then I have so many cities, I'm going to add all these distances. I probably don't need to really divide the whole term by n. I don't need to do that because whether I do this or not, the answer would be the same because divided by n is nothing but divided the whole thing by a constant. So in this case, minimizing the average distance and minimizing the total distance is the same. So here you may see again, you have square terms. You even now have a square root term. So the whole thing here is again nonlinear. So in all these three examples, we may see that we are having a very natural nonlinear program because the world by nature in many cases are just nonlinear. Okay? So the trade-offs can only be modeled in a nonlinear way. So that's why linear programming, integer programs are not useful in these particular cases. In general, a nonlinear program is always formulated in this way. I want to minimize some function subject to several constraints, and somehow some of these f or gi functions, some of them are nonlinear. Right? So this would be a linear program if all these functions are actually linear. This would be a nonlinear program if at least one of them is nonlinear. So here, some people may have different definitions about linear and nonlinear programs. So for linear programs, the definition is clear. All these functions should be linear. Some people would say, okay, nonlinear programs does not include linear programs. So they would say nonlinear programs are not linear programs. So typically, I follow this definition. I would say a program is either linear or nonlinear, but a nonlinear program is not a linear program. Okay? Some people would say, no, they don't think that way. They would say nonlinear programs actually contains linear programs. Or they would say any program is a nonlinear program. Nonlinear program is a generalization of linear programs. Some people would say that. So when you read articles, when you read textbooks, maybe you need to pay attention about their definitions. But anyway, I guess we all agree, nonlinear programs are much more general than linear programs. So that's why in many cases, we really need to do nonlinear programming. Okay, and that's also a very important part for this whole course. The course about formulating and optimizing nonlinear programs is called nonlinear programming. In general, the formulation would be easy. We don't need to worry too much about linearization. We don't need to worry too much about using integer variables to do this, do that, blah, blah, blah. So you probably still recall that in the previous lecture, when we are talking about integer programming formulation, there are many weird ways to deal with the constraints, big M, variables, blah, blah, binary, whatever. For nonlinear programs, formulating a nonlinear program is typically easy because actually now you don't have any restriction. But then optimization would be hard. So in this lecture, we don't really talk about how to solve nonlinear programs. We only try to show you, in many cases, you need nonlinear programming formulation. Okay? But still, we will talk about a lot of places, a lot of situations that you would be convinced that nonlinear programming would be really useful. Today, let's focus about formulation, and maybe in the future, let's talk about algorithms.